Okay, so we're kind of slowly moving along here, gathering, gaining information, knowledge. We're going to spend the whole lecture on what are called spherical waves today. And I might surprise you that we spend a whole lecture on this, but you will eventually see why. They're important for two reasons. One of them, they're the simplest type of diverging wave, okay, non-planar wave. And also, as we will see, there's a remarkable fact in acoustics that when you have a source that's radiating sound, and the size of the source is small compared to the wavelengths, the radiated sound is approximately a spherical wave. So if you don't get this, don't worry, we're going to go over this in depth in a few chapters from now. So anyway, here's what a spherical wave looks like. You can imagine, and we'll do this when we, a few chapters from now, imagine a pulsating sphere, uniformly pulsating sphere. Okay, so the radius is oscillating. It's always, at every point in time, it's a sphere, right? So it's going like this. It's not, and it's all in phase. It's a sphere, okay? And it's pulsating. It's going to send out a sound wave. It looks like this. On any concentric sphere here at any time, all the acoustic variables will be the same. Well, the particle velocity, of course, will change direction. The particle velocity is going to be going like this, right? So its direction will change, but the speed and the pressure and density change are the same on any concentric sphere. We call that isotropic. The sound wave here is isotropic, independent of direction. Far away from the source, as I think we discussed yesterday briefly, if you look locally here, you're sufficiently far away from the source, and you look locally here, you'll see you can see it here, you see approximately a plane wave. And we've talked about, this will be a plane traveling wave approximately. And we've talked about that. So the work that we've done with traveling plane waves, we have to be connected to that here. This is going to be a check on our calculations here. The wave has to reduce far from the source. It has to reduce to a traveling plane wave. Now, there's one, I want to make sure you get something here. It's simple. But you can imagine these lines here are crests of the wave. This is a wavelength here. This distance, I didn't draw it in here, but we have some distance. We're measuring the distance r from the center of the source here. When r is much greater than lambda, we're going to have approximately a plane wave. Right? Now, it's not, theoretically, it's not convenient for us to state this. What we state, in terms of this dimensionless quantity kr, this is the relevant dimensionless quantity here, the wave number. K is, of course, just 2 pi over the wavelength. So these are equivalent, they're roughly equivalent here. But this is the clean theoretical way to state it rather than this. But in your head and physically, you want to think this. But usually this is how we write it, okay? Because in the math, this combination will occur when we make mathematical approximations. But physically, you want to think of it this way. Okay, now, it is, I've drawn an outgoing wave here. Right? You can have an incoming wave. You can have an incoming spherical wave. These are not very common. These are much more common, outgoing waves. So we're going to focus our attention on outgoing waves. But it's not, if we wanted to include it, it's not that difficult to include. And I'll show you the basic thing you need to do. You just change a sign in the phase factor. There is a very important application, though, of incoming waves. And that's in what's called single bubble sonoluminescence. I don't know if you've ever heard of this, but if you if you can acoustically cavitate a liquid. If the pressure, if you have a resonator, this is how they do it. You have some kind of flask here, and you got some water in here, and you have some piezoelectric drivers here. A standing wave mode is driven here, and it can self-cavitate, or it's actually cleaner to introduce a little tiny bubble here, typically microns, little tiny bubble here. And what can happen is they're driving a standing wave of sound here. What can happen is the bubble can, when the pressure swing goes negative here in the acoustic wave, the bubble expands. And going the other way, when the pressure swings to maximum, it contracts, right? It's not difficult here for these oscillations to become extremely nonlinear. And what happens is the bubble expands and crashes down. Okay, this is not sinusoidal motion. At small amplitudes, the bubble will be oscillating sinusoidally. It crashes down here. And as it's coming down, the surface of the bubble will generate a shock wave, an incoming shock wave. So it's a spherical wave that's coming in. And that's important because when the bubble crashes down, there's so much energy concentration that light can be emitted. And you can see it with the unaided eye. This was actually discovered in the 70s, but it didn't really go anywhere. And then it got rediscovered in the early 90s, and it became an extremely hot topic. Well, hot is not the right word here. The bubble is getting so hot. The reason I shouldn't use the word hot. The bubble is getting so hot when this incoming wave crashes down that light is emitted. So people viewed it as a possible source of fusion. Star in a jar. You guys, have you ever heard of any of this? This was all over the place in the 90s and well into the 2000s. Scientific American. It was in the New York Times. Okay. You've never heard of it, right? Okay. Yeah. Well, obviously they weren't successful in achieving fusion, right? Although some people claim to have seen it, but and even if you can achieve fusion, then you have to put it on a commercial basis, right? So this is the little tiny volume right here. So even if you could achieve fusion in here, so the idea is it's getting so hot, maybe it'll be like a little sun, right? It fuses, the energy is released due to the fusion of hydrogen into helium, basically. So anyway, that's an example of it. That's an important example of an incoming wave. We're going to focus on outgoing waves. So we'll talk about, I already talked about this. So how do we handle this analytically? Well, the wave has to satisfy the wave equation, and the wave equation involves the Laplacian, right? And if you look up the Laplacian in spherical coordinates, you can derive it if you want. That's an interesting little task. Most people just look it up. Here's the Laplacian in spherical coordinates. And you remember what spherical coordinates are, right? If these are rectangular coordinates, x, y, z here, the distance r is the distance from the center here to some point. The polar angle theta is the angle made by this line right here from the z-axis, okay? And then phi is the azimuthal angle, which is measured from the x-axis here. So a circle concentric with the z-axis right here and parallel to the xy plane, a point moving around on this circle right here will have constant r, constant theta, but phi will be changing from 0 to 2 pi, okay? I'm sure you've all seen this. I just want to refresh your memory. Now, for spherical waves, this is quite complicated. However, we have an isotropic wave here. The acoustic variables only depend upon r and t. The pressure, for example, the acoustic pressure, and this doesn't have an arrow over it. This is the distance. This is the r coordinate, the distance from the center. And similarly with the other acoustic variables. So these are gone. There's no angular dependence due to the isotropy. So this is all we have to deal with.
I'm sorry, can you repeat that? Why is there no angular?
See, this wave is traveling spherically outward, right? If at any time you look at the pressure at a point here, the pressure is going to be the same at every point along a sphere here. So the pressure is only a function. It'll vary in time. If you're sitting at this point and the wave is passing over, you're going to see the compressions and expansions. But it's not going to be. It's only going to be a function of the distance r, due to the isotropy. So there's one way to handle this. There's kind of a trick that you can handle. The way that you can handle this here is to notice that the radial term here, these two can be combined into a single operation, and it's best just to write it down, and you can verify it. When you take, I'll let you verify this. It's simple to show, but you can do it in your head actually. It's easy to see that these two terms combine into that. And the way people usually look at it is you start from here and go this way, okay? And if it's hard for you to see, it's a little difficult for me to see right now, I have to admit, but you can just write it out. It's easy to show that this is true. And the advantage of this is that if we now go to the wave equation is the Laplacian on the pressure minus c squared times 2 time derivatives. That's the wave equation. The Laplacian has come down to just this. Here's the Laplacian. Whoops, over here. Sorry. Okay, yeah, I'm sorry. I flipped things here. KFCS do it this way. So the way they write it, the wave equation is going to be this, okay? And for our spherical waves, we can write the Laplacian, because of the isotropy and because we can combine these two terms, we can write it like that, so we get this. And what do you see when you see this equation? This is the whole trick here. Does that equation look familiar? Yeah, it's the wave equation. Forget the RP here, just call that psi or something, okay? We have the wave equation for the quantity psi, for RP. So we know it in one spatial dimension. So it's like strings. So we can immediately write down the solution. The general solution is that there is the general solution for RP. This is emboldened because we've gone complex here. The general solution is we think of it as a right traveling wave with some arbitrary amplitude plus a left traveling wave. Now in our case, a right traveling wave is an outgoing wave, because as time, to ride a wave here, to be at a point of constant phase, like a crest, as time goes on, you want to increase R. Right? There's the other solution here has a plus sign. That's the incoming spherical wave, which we're going to ignore. We're just going to deal with outgoing waves here. So this is nice. We can utilize our knowledge of the one-dimensional wave equation to get the solution. Now we just divide by R, and we get this expression for an outgoing spherical wave. That's what the acoustic pressure looks like. It's got the usual phase factor here, the wave factor. We know that's going to be there, right? And you can see that the amplitude falls off proportional to the distance. Why is that? I mean, the math is telling us that, but it's important to look for physical reasoning for this. Incidentally, before we get into that, we can have an arbitrary this is called the complex amplitude, arbitrary complex amplitude here. In the end, we're going to take the real part of all this, right? For the actual physical pressure, we take the real part. So the amplitude of the pressure is inversely proportional to R. Why is that? Well, if we look far away from the source, sufficiently far, if we're out here, we have an approximate plane wave. I know that the energy passing through a sphere. So here's our source. I'm going to draw a sphere right here. And let's consider another one over here. the power, the acoustic power, here's our center, where the source is. The acoustic power, the total power going through this just mathematical sphere here, has to be the same as the power going through this sphere, right? That's energy conservation. We focus our attention on this region right here. There's energy coming into this region. There's energy exiting that region. The incoming energy has to be the exiting energy, because we're not dealing with any absorption here. Now, in general, the energy coming in will be greater than the energy going out because you're losing some acoustic energy. It's heating up a little bit, you know, due to viscosity. But in our model here, we have no losses. So energy's got to be, the acoustical energy has to be conserved. So this means that the power here, the power going through here is going to be the intensity times what? This is the intensity is the power per unit area. We need to multiply by the area. All right, with this R right here. So to find the energy coming out of this, through this surface right here, this spherical surface, it's going to be the intensity here times 4 pi r squared. If we have the same power coming out here, how is the intensity going to have to behave here? The intensity is going to have to fall off because we have greater area, right? In fact, how must the intensity fall off? It's got to be proportional to what? 1 over r squared, okay, by energy conservation. Now, out here, we know what's going on, and we have knowledge, specific, quantitative knowledge of what's going on out here. We know that the intensity is proportional to the square of the pressure, right? We derived that yesterday, I guess. So, because the intensity is proportional to the square of the pressure, how must the pressure fall off here? It's got to be 1 over r, all right? Now, we can't really extend the argument down here yet because we don't know we don't know what the relationship between the pressure and the intensity is here. We just know it for a plane wave. But that's one of the main things that we're headed for in this lecture, all right? So anyway, at least far from the source, it's very reasonable. And in fact, it has to be. It's more than reasonable. It has to be. Far from the source, we have to have the pressure falling off as 1 over r. Now, the solution is telling us that it falls off for 1 over r right down to the source. So we're going to have to see how that comes about when we calculate the intensity down here. But that's getting ahead of the story. The next thing we need to look at is the particle velocity. Okay? So we have this acoustic pressure here. Sorry. Here's our acoustic pressure. We'll find the particle velocity here through the velocity potential. If you look back, you'll see that for linear acoustics, this is the relationship between the pressure and the velocity potential. These are emboldened now because in general they're complex, P and P. This comes from, we got this from Euler's equation. If we know that everything is going, in time, everything is going like e to the I omega t here. So we can just simply replace the partial time derivative here with I omega. We can then algebraically solve for phi, and we get this. You can do this in your head. So here's the velocity potential. And now we need to take the gradient. All right? And the gradient, we have an isotropic wave here. The gradient is just going to be the r derivative. And the direction is going to be straight outward. Or in, there can be a plus or minus sign due to the phase factor here. So the gradient essentially reduces to the r derivative here. And then now we see something that's important. We won't fully realize the importance of this until a couple chapters from now. But I need to point it out to you right now. Phi behaves simply. It's proportional to the pressure, right? Proportional to acoustic pressure. So it's just 1 over r. It's what you want a spherical wave to be. It's the simplest reasonable spherical wave. It's got the phase factor and it falls off with distance. What's going to happen when we find the particle velocity here? Do you see how it's going to be different? When we differentiate with respect to r, we've got r occurs in two places here, so we're going to get two terms. The particle velocity is not simple here. It's not going to go simply as 1 over r with the phase factor. It's not going to be. Okay, so let's go ahead. We can do the derivative. Well, I think I've skipped a little step here, but it's simple. It's simple algebra, simple differentiation. So we use the product rule, of course, right? I differentiate this, multiply it by this, and then I add to that this multiplied by the derivative of that, right? The simple product rule for differentiation. We get two terms. We can write them like this. All right, and like I said, I've skipped one step, maybe two, but they're very simple steps here. And you'll notice we've gotten the pressure back here. Here's the pressure. So let's go ahead and write it like this. You can write it like that. And now you can see here, the velocity is not simply proportional to 1 over r. The pressure amplitude is proportional to 1 over r. So the velocity amplitude is going to have a 1 over r in it, but it'll also have a 1 over r squared. And that has big consequences. We won't be able to see them today, but we eventually will when we get more deeply into this. Now, at this point, it's good to check. How do we know this is right? You know, well, you might say, well, it's in the book, and the book's in its 4th edition, so it's probably right. Yeah, that's one way of approaching it, okay? But what if you're doing research? You're doing something nobody's done before, and there's no book, no answer in the back of the book, or whatever. So you always want to check. You always want to look at special cases. We'll be, I don't think I've emphasized this yet in here, but throughout this course, we're going to be, when we get some result, we're going to be looking at it in special cases. And the natural special case here is Kr much greater than 1, which means we're many wavelengths away from the source. We know in that case that locally we're going to have a plane wave. So, and we know what the relationship between the particle velocity and the pressure should be. So do we get that? When Kr is large, what happens to this term? We neglect it, and we get U is equal to P over rho naught C. That's right. Usually we write it the other way, right? P is equal to rho naught CU. It's equivalent, obviously equivalent. So that checks. Our solution checks in the limit of large Kr. And again, from a research perspective, the reason this is important is that if your general expression, more general expression here, doesn't reduce properly in a special case, there's no point for you to go on. You've got to go back and find your mistake. If this didn't check, we would have made a mistake, clearly. The spherical wave has to reduce to a local plane wave, sufficiently far from the source. Now, when we are, I don't know if I said it in here, but when we are far from the source, then they're both falling, the particle velocity and the pressure are both falling off as 1 over the distance. Okay, but it's only far from the source. We've gotten rid of this term because we're far away. Near to the source, the particle velocity will not be exactly proportional to 1 over r. Okay, now, I can't remember how much, I don't know if you use impedance a lot in 31 in the previous course. I can't remember. It's been 2 years since I taught it. Seems like a really long time ago. You guys felt like you used impedance a lot in the previous course? What's your feeling?
We definitely used it.
Yeah.
I'm not sure about it a lot. But.
As I've mentioned to you, I think before, we're going to use it a lot here. Okay. In fact, this is our first case where it's going to be very useful. So I want to tell you, we're going to form the impedance here for a spherical. This is for a spherical wave. It's easy for a plane traveling wave. And why are we doing this? Well, the main reason, one of the reasons, and probably the main reason here, is that the pressure is simple. The particle velocity is not. hard to deal with the particle velocity. However, once we know the impedance, once we've calculated the impedance for a traveling spherical wave, when we've done it once, we can always go back to that result. And if we want to get the particle velocity, we can get it from the pressure, which is simple, just by dividing by the impedance. So that's sort of the main reason that it's useful here. It allows us to get the particle velocity without going back and recalculating or looking up a formula. The impedance here is simpler. It's not simple. I have to tell you, it's not simple, but you'll get used to it. This is just, the particle velocity is just complicated to deal with. So let's form the impedance here. It's the ratio, pressure to the velocity. And of course, these are complex, right? We deal with a complex, our impedance is defined to be complex here. It's the complex pressure divided by the complex particle velocity. And the reason we go complex is there can be a phase between these two. And if you're guessing we're going to have a phase here, you're right. You know, once you get away from this simple plane traveling wave, there's going to be a phase between these two things. So we want to deal with a complex impedance. We need that. That phase information is vital. I'll be able to show you today why the phase is vital. Okay, so this looks simple, right? We could stop here, but this is not easy to work with. It's got a complex denominator. So one thing you can do is you can express this as real plus imaginary parts. And we got names for those here, right? What's the real part of the impedance? It's the resistance. The imaginary part is the reactance. And those are very physical quantities. They have definite physical meanings. Those of you who've had some electrical circuit theory probably know this, but we're going to go through that in this course. It carries right into acoustics, why we call them resistance and reactance. There are reasons there. So we've got to clear out this denominator. And the standard way to do it, here I've just rewritten it here, is if I'm going to multiply this by 1. I don't want to change its value. And what I'm going to choose as my representation of 1 is this quantity. Why do I choose that? Well, you can see when I multiply any complex number here by its complex conjugate, I'm going to get a real number. So I'm clearing out the denominator. I'm making the denominator real. So we do this. Here's our real denominator. We get this. Gather terms into real, it's really simple here, into real and imaginary parts. So here's the resistance, the real part of the impedance of a traveling spherical wave. And here, the part that's multiplying the imaginary unit is the reactance. And now what's the next thing that we do? We check it, right? So we know that when we're far away, let's see what we get when Kr is large. What happens when Kr is large here? Well, I can neglect the 1, and then what's this? That's 1. So I get rho naught C. And what happens when Kr gets large here? 0. It's 0. It all works out. We get rho naught C for the impedance. And again, if it hadn't worked out, there would be a mistake somewhere. So we're going to actually use this very, very soon. But this is a pretty complicated representation of the impedance. Okay, when we have to use it, we'll use it. The simpler representation, instead of a real plus an imaginary part, you can also represent any complex number as a modulus and a phase, right? So this denotes the modulus or amplitude and a phase. You all should be familiar with that. Okay? So we're going to work, this is simpler. We're going to work with this more. It's easier to work with. So let's determine that representation of the impedance. So first of all, the modulus, or the amplitude, I'm going back to the beginning here, I see. I need to take the modulus of this. I multiply through by Kr. What's the modulus of this? This is from Pythagoras. We know what this is from Pythagoras, right? It's going to be the square root of the square of the real part plus the square of the imaginary part. Okay, just think of this as plane geometry. This is really plane geometry here. Okay, where this is the y-axis is the imaginary axis and the real axis is the x-axis. So that's going to give me this. That's the modulus. Okay, it looks a little complicated, but we'll be able to express this in a simpler way in just a moment. What's the phase? We also need to know the phase. Oh, I think so here, any complex number here, I guess bold, I should put it in here, will have this representation as the modulus times e to the I theta. Now, this causes trouble with students, and I think I skipped this. Oh no, maybe it's coming up right now. Yeah. Okay. Yep. Okay, that's good. You see this theta right here? This is what KFCS use. It's called the argument of a complex number. It's this angle right here from the real axis. Wow, who's into colored chalk? Is that Clyde? Was Professor Scandrett into colored chalk, Les? Did you have a chalkboard in the VTC room? I don't think there's a chalkboard in there. Yeah, so you wouldn't. Well, it can now be revealed. I think Clyde is the one behind this. Okay. Anyway, we have a real axis and an imaginary axis. This is called the argument. It's this angle here. This has absolutely nothing to do with a spherical coordinate theta. That's gone. We have an isotropic wave. So I know from my experience that students will confuse this theta with the spherical coordinate theta. They're completely different. And this, so I hit this years ago and I said, oh, we should change this to like alpha. Well, the problem is this is throughout KFCS. They use theta here. They use it. So I figured we just have to live with it. All right? But I want to make sure this is clear that this has nothing to do with the sphere. This is the complex angle here called the argument. Okay. So you can see here that the tangent of theta is the imaginary part divided by the real. It's an angle whose tangent is the imaginary part divided by the real part. So that's nice. We just calculated those. If you go back and look at this, it's really simple. When you take the ratio of the imaginary part to the real part, it gets real simple. It's just 1 over kr. So there's our angle. And here's my warning right here. I thought it was earlier, but here it is. This is an appropriate place to have it. Okay. Now, I strongly encourage you to. We're going to be doing a lot with spherical waves because they're the simplest diverging waves. In fact, as I told you, when you get beyond that into other types of waves that are not planar waves, real complicated. Cylindrical waves, for example, are not simple. And they're in KFCS. We're not going to get into those. I'll just make a comment about them, make a few comments about them. But they're in there if you ever need to deal with them. Let's see, I didn't have there's something I forgot to tell you guys the first day. This book is it's supposed to be a dual use book. Anytime somebody tells you something's dual use, no matter what it is, I suggest you just walk away. This doesn't work. Okay? Okay? Sounds good, usually doesn't work. This is supposed to be for researchers as a reference, and it's also be for students the first time through. Now, do you think that's going to work? No, it doesn't work. So, it's tough because it is a common book used by acousticians as a research book, okay? To get information. It's tough on students the first time through, right? So why did I can't remember why I got kicked into that. I saw something, well, there was some connection, I've lost it. Anyway, it's good for you to know that, okay? So that's one of the reasons that I paid careful attention to these notes and type them all up, because this is a lot simpler than the book, okay? But you probably know that by now and you should expect it. The textbook is it's hard for a student. It's difficult. So somehow this triggered me into it. We're going to be doing this, we're going to be dealing with spherical waves a lot. And there's a nice simple triangular construction here that allows you to get these quantities. You'll notice theta is a function of r, right? The phase here. And theta is the phase between the particle velocity and the pressure, because it's the phase of the impedance. So it's the phase angle. There's a phase between they're not in phase anymore. It's only for the plane traveling wave. So to quantitatively handle this, it's appropriate to remember this diagram right here, because you can see that we can get that the tangent of theta is what? It's 1 over r. So this is correct, okay? And Pythagoras tells us what the hypotenuse is here. So one of the reasons this is useful is, look at our modulus. We're going to get some use out of it right now, and we're going to get use out of it when we do problems. Look at our modulus here. What is this quantity right here? What is Kr divided, what is the adjacent side divided by the hypotenuse? That's the cosine of theta. So we can write this as simply the cosine of theta. And that's how it's typically done because it looks simpler. But the complication is in there. So this is the way we usually think of the impedance of a traveling spherical wave. We use it in this form. It's complex, there's a phase, and here's the modulus or the amplitude. Now, when you want to deal with this, ultimately what you need to do is you need to get back to Kr, almost always. We got to get, and how do we do it? We do it from this diagram right here. So I think this is really important. That's why I took the time to draw it in Word. And drawing anything in Word is unpleasant, especially if it's Word for Macs. I don't know if any of you know this, but all these diagrams that you see in the notes, ugh, trouble, a lot of trouble. Okay, now, just to point something out, often all we'll care about is the amplitude, okay, called the peak amplitude, called capital P, capital U. When we just take the modulus of this, because the modulus of the impedance Z is going to be the ratio of the amplitudes here. The phase factor goes away and we get this. So this is our expression for the relationship between the amplitudes. And it looks a lot like the plane wave, doesn't it? The plane traveling wave. That's what it would be for a plane traveling wave. But it's got this cosine of theta in here. And theta depends upon the distance from the source. In fact, that brings up the next thing. We need to check this. So there are two limiting cases here. There's far away, right, that we've already talked about. And far away, we've actually already talked about that. That's called the far field. But let's do it again. I don't know if I do it in the notes again. Let's check it again. Well, I say as discussed before. I think we ought to look at this again from the triangle perspective here. What happens, and I want to make a note of this. Yeah, I think we should do it. So we have this relationship here. What happens when Kr is much greater than 1? What's the difference, the fractional difference between the hypotenuse and the adjacent side here? What happens to theta when Kr becomes large? It's small, right? Because this becomes small compared to that. These two become approximately the same length. So theta goes to 0. When theta goes to 0, what do we get? We get the right answer. We get the traveling wave answer. Okay, so it works there. Now, what about the other case? Oh, the idea here is this. This is complicated. I think everyone accepts this. It's complicated. So to appreciate complicated things, often we look in special cases to try to get a physical feel for what's going on. So the other case here, where things are going to simplify, and this happens in practice, as we will eventually discuss a few chapters from now. What happens when Kr is much less than 1? We haven't talked about that yet, but it's just the opposite limit from the Kr much greater than 1. So here you're close to the source compared to the wavelength. There's extreme curvature now. It's not, the wavefront's not flat. So what happens? This is called the near field. And what does our theory tell us? Again, we go to the triangle diagram. So now when Kr is small, what happens? Now the hypotenuse is approximately 1. So now what does our triangle look like? Instead of our triangle being a sliver, coming down like this, now it's close to, this theta is close to 90 degrees. It's almost 90 degrees. That is significant. When the phase difference between the pressure and the particle velocity is 90 degrees, what's the intensity? Remember the intensity, right? Remember the intensity is the time average of these two quantities. And if they're 90 degrees out of phase, this is 0. And we're going to discuss that right now. That's important to get a physical feel for this. So I think I have a, oh, it's not right now. It's coming up in the next section, okay? So what we're finding here is a general fact for all wave systems. All, I should say actually linear wave systems. Because when you go to nonlinearity, it turns out you can beat this problem that I'm going to discuss to you here. And the Navy knows this well. It's called a parametric end-fire array. I don't know if you guys have ever heard of them. They're used as fathometers. What's being utilized there is a nonlinear effect to create a beam of sound. But that's nonlinear. For linear waves, what we've found here is if you're very close to the source, let me back up a little bit here. If you're very close to the source, that means you've got a small source. You know, if I've got a big source, I may not be able to, I can't reach here. Okay, so this means the source is evidently small here because I'm just a fraction of a wavelength inside the source. So the source is not big here. We have this small source, small relative to a wavelength, okay? And it's emitting sound. And we find here that the intensity is very small. A small radiator is a poor radiator. Have you ever heard this before? Or something similar? It's true. It's true for all waves. Okay. You have a big problem here, and I'm not being real precise about that now because it's going to have to wait for a few chapters from now. But I'll remind you of this. I want you to realize right now that what we're seeing here is that when we are close to this source, when we have this small source, only for a small source can we get here. Otherwise, we'd be going inside the source. It's the only way you can realize this. We're going to get very little radiation. So we'll go over this in depth later in the course. Okay, so where we're headed here is the intensity. We want to look at the intensity of spherical waves. And in particular, we want to get an expression for the total power radiated from a spherical wave source, acoustic source. So let's calculate the intensity here. Here's the expression. This is the general expression as we discussed yesterday. We can abbreviate it like this with these brackets. It means the time average. And now I panicked yesterday but the notes they're fine. I don't think I'm going to change them on this. But at this point, we have to do the time average of the pressure times the velocity. You've got to take the real part of the pressure and the real part of the velocity. You can't time average the product of the complex quantities and then take the real part. And it's as I mentioned to you yesterday, it's easy to see this. I'll let you come up with an example. Just play around with a couple of complex, just pick two complex numbers, make them simple. You'll find that you can't multiply, you can't commute these operations of forming a product and taking the real part. Here I formed the product and then found the real part. That doesn't give us the right answer. The right answer is you've got to take the real part, you've got to put the physical pressure in here, the physical particle velocity, and then multiply them. If you have trouble with this, just get in touch with me. Okay, so to do this, the first thing we're going to do is we have this general pressure that has a complex amplitude. We can assume without loss of generality that the amplitude of the pressure wave is real, a positive real number. Okay, there's no problem in this case. So let's do that for simplicity. Here's our pressure. We've got to take the real part, and this is easy. It's just going to be, as you know, it's going to be this. Okay, now we're going to abbreviate this. You have to be careful about this. This pressure amplitude here is a function of R. It's equal to A over R. A is a constant. So the pressure amplitude is falling off as 1 over R. But it's just convenient to lump it all in there into this pressure amplitude at some distance R. We need to find the velocity to find the intensity. How do we find that? Through the impedance, right? So we need to take the real part of each side here. So we take the real part of this. So we need to take the real part of this. I've taken the pressure and divided by the impedance. You'll recognize the impedance there. And now how do you handle this? Well, what you want to do here is you want to notice that we can absorb this e to the I theta. We can bring it upstairs and make it e to the minus I theta, and then absorb it into here, into the phase factor. So when we do that, oops, we get this. Now, I see what I've done here. You see what I've done here, just to make this look simpler? What is this capital U? Well, that's the particle velocity amplitude at some distance r. It depends upon r. And it also has this cosine. Remember, theta depends upon r. So that's all buried in this u here. Okay, you can see it from this expression. This u is going to be given by all of this right here. You can see it from here. Okay? And we really need to do that, and you'll see why on the next page here. Oh, I explicitly stated it here. Okay, now again we're seeing, because theta is a function of r, the particle velocity amplitude does not fall off in general as 1 over r, because theta is a function of r. So here we go. Here's the intensity. We multiply the actual pressure times the actual particle velocity, we get this, and we time average. It's convenient to use the bracket notation here. Now, the amplitudes are only a function of r, not of time. So they're not involved in the time average. So what I can do is, I can see this p and the time average here? I can just take p and u, I can take them out. They only depend upon r. This time average is done at a fixed r. So I can take those out. That's what I've done here. And I've also said, look, I don't want to carry this along, omega t minus kr. Let's call it something, let's call it tau. So our time average over t is not going to be a time average over, it's going to be an average over tau, the quantity tau. So I can boil down the expression to this. This is what we need to determine. And now, you've got to use a trigonometric identity. Most of you would guess this, I think. To beat this down to some useful expression, we're going to use the cosine of the difference of angles. Here it is. You've all seen this. When I substitute that in there, I get this. Now you'll notice I've done something here. When we take the time average here, I've taken the cosine of theta, I factored the cosine of theta out because it does not depend upon tau. Keep saying time average, but the average over tau. So the bracket just involves this. Now, what's the average of the cosine squared? Can you see it? When we talked about it, I think it was yesterday? 1/2, right? That's easy. What's the average of the cosine times the sine? Yeah, so do you guys know this from or just know it from other courses or from last quarter? Okay, but this is so important that I want to talk a little bit about it here, okay? And that's what's on the next page, I think. Yeah, now, here's the analytical approach, but I encourage you, this is what people do and they want to make sure they're right. But when we think about this stuff, we think about it like you guys were just thinking about it. Okay, the average of the cosine squared is 1, the average of the sine times cosine is 0. You were thinking about it probably graphically. Okay, I don't know, maybe. But analytically, this is really simple. The average of the cosine squared, we saw this I think yesterday or the day before. We use a double angle formula here, and we find that the value is 1/2. Here, we use a double angle formula. The cosine times the sine is 1/2 the sine of 2 times of tau. And the average of this is clearly 0. Okay? So what's happening graphically here, and I encourage you to think of it this way. We've already talked about the cosine squared, or the sine squared. Here's a cosine. I'm just doing over half a period here. That's all we need. Here's a cosine. Here's a sine. When you multiply these two things together, you're going to have a positive quantity here. You're going to have a negative quantity here. And for every value, if you're at some point here, when you multiply these two things, you get a value. If you go diametrically on the other side here, the absolute value is the same. When I multiply this times that, I'm going to get the same value as that times that by the symmetry and anti-symmetry here. So the product here is, it swings positive and negative equal amounts. The average is going to be 0. The time average has to be 0. And if it's ever in doubt, you always just go to the analytics here, right? So this was a graphical proof of why we got 0 here analytically. Okay, so here's our result. The intensity if you look back, what we've done, plug our result in for the time averaging, here's what it is. This, some of you may recognize this as particularly in circuit theory. Transformers, voltage times current with a cosine of an angle, that's called the power factor. Maybe you've heard of that. But a remarkable thing happens here. We'll tend not to use this, but this is, we can recast this. We can use this result, with the relationship between the pressure amplitude and the particle velocity amplitude. And we can rewrite this like that. And now something really remarkable has happened here. KFCS, I don't think, get excited about this, but to me it's really exciting. Do you recognize this? This is the intensity for a plane wave, plane traveling wave. Right? So what we've found is here, this is spherical waves, which are complicated. We've found that in terms of the pressure, which is simple, you can use the formula for a plane traveling wave. We just derived it here. It's the same. And I think that's remarkable. Okay, and why does it happen? Well, the only thing I can think of is we know that far from the source you have to get this. Because far from the source you have a plane wave. The fact that it maintains this, we have the same formula here as you get closer and closer. I think what's happening here is we have to conserve energy conservation. And we have a pressure that's going like 1 over R, exactly. The pressure goes exactly like 1 over R. That's one of the first things we did in the lecture here. And apparently the only way to conserve energy is that intensity also, the intensity has to go as 1 over R squared. Now that I think about it, the intensity has to go as 1 over R squared. And the only way to get it is here. We go through this long calculation and we end up with something that I guess, now that I'm thinking about it, I guess we could have just asserted this. I'll have to think about that. But anyway, it's true. And now finally, the final step here, and we'll make a lot of use of this. What is the total power, acoustic power coming from our source? This is almost always an important quantity in acoustics, as you can imagine. What is it? Well, now that I know the intensity, I just multiply it's isotropic. I just take the intensity, which is the same at all common distance from the center. I just take the intensity, divide it by the area of the sphere, the radiation's going through. I get this formula. Now remember, P is A over R, so we can combine these to get this. KFCS used capital pi for we'll do that to the total power. This is the total power output of a sphere, a pulsating sphere, with a pressure with this A with a pressure amplitude. We'll connect this, we'll make this more physical later on, in a couple chapters from now. But we'll go back and use this a number of times in this course. Any quick questions? We're a little over. Quick questions? Okay, so tomorrow's problems, right? And probably a quiz. To be honest with you, I haven't checked yet, but I've got a feeling I'm going to be sending out a quiz tomorrow. Or posting a quiz tomorrow. Okay, yes?
You also posted the problem set. Do you want us to give it to you?
You guys give me a hard copy. The students, they're posting it on Sakai. In fact, I don't know if I allowed you to post it on Sakai. I think in Sakai I have 2 groups. Jeannie and I have 2 groups that we deal with. Yeah, you guys want to just submit a hard copy to me, right? Yes.
Yeah.